Hello and welcome to lesson 5 of our study in integral equations 1. So in this line we'll be talking about degenerate kernel. Note that in our third lesson we talked about separable kernel, how to solve our integral equation when we have a separable kernel. So in this lesson we'll talk about when you have a degenerate kernel. So how do we say our kernel is degenerate? So our kernel Q of xt of an integral equation is termed degenerate if it can be represented in the form of a finite sum of pairwise products of functions, one of which is a function of only x and the other being a function of only t. So mathematically, if we say our kernel is degenerate, then it means our kernel can be written in this form. Alright, so you see we have two functions multiplying each other. There's a function of only x and there's a function of only what? T. And you have a finite sum, so from 1 to n. So this is the expanded form. So from the expanded form we can write it in the compact form, and this gives us the compact form. Okay, so where our ai of x and bi of t are linearly independent functions. Okay, so this is what we mean when we say the kernel is degenerate. Okay, so if this concept is well understood, then let's move on. So let's go through the solution of a Fredholm's integral equation with a degenerate kernel. So when we have a Fredholm's integral equation and the kernel is degenerate, what are the processes we go through to find the solution? So let's consider the integral equation below, the standard form of an integral equation. So equation 1. Okay, so if the kernel ks of t is degenerate, then it means it can be written in this form. Alright, we've explained what degenerate kernels are, and when we expand them we can have something in this form. So let's name that equation 2. So we'll come and put the whole of this inside equation 1, where we find kx of t. So doing that gives us this. So y of x will be equal to f of x plus lambda integral from a to b. Then the whole of this now happens to be our kernel, since it is degenerate. Alright, so after that we can expand. Okay, because the whole of this and the whole of this are multiplying what we have inside, so we can expand. So expanding them is going to give us y of x will be equal to f of x plus lambda integral from a to b, a1 of x, b1 of t, y of t dt plus this up to what we have our m term here. Okay, so you can see that we are integrating with respect to t. So it means the ai of x's, or the functions of x's, are all constants. Okay, so that means this will be a constant, this will be a constant, and this will also be a constant. So we can pull that one out. So pulling our constant out, you are going to get y of x will be equal to lambda e1 of x, then the whole of this. So we pull all of them out and we get this. So when we get this, what we do is that, we have a definite integral here. So we decide to name them c. So ci's. So we name this one c1, c2, and cn. Okay. So doing that is going to give us y of x will be equal to f of x plus lambda e1 of x. But the whole of this, we are now naming it c1. So c1 plus lambda e2 of x, c2, up to lambda an of x, cn. Okay. So this happens to be the solution to the integral equation as far as we can find our c's. Okay, so we can write that in a compact form. So this happens to be the solution, and we can write it in the compact form. When we write in the compact form, we will get the compact form. The general solution is y of x equals f of x plus lambda to be summed from 1 to n ai of x, then integral from a to b, bi of t, y of t dt, where our ci's will be given by this. Okay, so the whole of this is our ci's. Okay, so now that we've gone through the process, let's try to solve two examples with what we just did. So the question 1 says you are supposed to solve the integral equation y of x minus 2 integral from 0 to 1 plus 3xt y of t dt equals s squared. And the second question says we have to find the exact solution of the integral equation y of x equals negative 8x minus 6s squared plus integral from 0 to 1 20xt squared plus 12s squared t y of t dt. So let's take the first question. So our integral equation was given to us in this form, but we would want to put it in the general form, the standard form that we know. Okay, so in doing that, then we have to take this and send it to the right hand side. So doing that is going to give us y of x will be equal to s squared plus 2 integral from 0 to 1 plus 3x dy of t dt. Then I want to find out which of them is our kernel, our investigative parameter lambda, free or forcing term. Okay, so we have to compare it to the general form of our integral equation, the ones that we know. And there's it. So making our comparison, it means our free term or forcing term f of x is s squared. Our investigative parameter lambda is 2. And our kernel is 1 plus 3xt. So now, before we can solve this problem using the method we just discussed, we have to find out if indeed our kernel is degenerate, because it is only when our kernel is degenerate that we can solve it with that method. So we have to go through that process. So we have to show that our kernel k of xt is or degenerate. So note that we just have two terms here. So the first term, the second term. So that means we can write our k of t as a1 of x, b1 of t plus a2 of x, b2 of t. And from the question, a1 of x, b1 of x is 1, a2 of x, b2 of t is 3xt. So now we have a1 of x, b1 of t is equal to 1. So that means we can say that a1 of x is 1, and b1 of what? T is what? 1. Since 1 times 1 will give us 1. Then when it comes here, we have a2 of x, b2 of t equals 3xt. So we can say that let a2 of x be 3x and let b2 of t be what? T. Because when you find a product, you will get this. So that's what we have here. Okay. So because we've been able to put our kernel in this form, it means that our kernel is degenerate. So since it is degenerate, then we can go through the process we know to find the solution. And note that the general solution is given by this relation, where the whole of this is our ci. That's what you can see here. So here, since we only have two terms. Okay, that means our I is going to run from 1 to what 2. So the general solution for this particular question, since we have two terms, is going to be y of x equal to f of x plus lambda a1 of x, then the integral from a to b1 of t y of t dt, then plus lambda a2 of x, the integral from a to b2 of t y of t dt, where the whole of this is our c1 and the whole of this is our c2. So that's what you can see here. So making that substitution, it means you are going to have y of x will be equal to, so let's make the substitution here. So y of x will be equal to, so our free or forcing term is s squared. So that's what you can see here. Our investigative parameter lambda is 2. Our a1 of x is 1. So any number times 1 is the same thing. And this is c1, the whole of this. So that's what we can see here. And here, our investigative parameter is what 2. And our a2 of x is what 3x. And this is c2. So that's what we can see there. So expanding, you're going to get s squared plus 2c1. Then 2 times 3x is 6s times what c2. So that means this happens to be the solution. But I hope you can see that it happens to be a general solution, not the exact or the particular solution, because we have constant c1 here and c2 here. So we have to find these to make sure we have the exact solution. So what we do is that we do change of variables, and so we change x to t, so that instead of having y of x, we can have y of t equals t squared plus 2c1 plus 6c2t. The reason why we do that is that when you are finding for our c's, we need y of t, and not y of x. So that will help us to be able to know what y of t is, so that we can put it into the integration and solve to get our c1 and our c2. So changing variables is going to give us y of t will be equal to t squared plus 2c1 plus 6c2t. So putting it inside, we're going to get c1 will be equal to, c1 was equal to integral from 0 to 1 b1 of t y of t dt, and b1 of t was 1, y of t is this, so you make substitution, then dt. Okay, so that means you are going to have the integral from 0 to 1 t squared plus 2c1 plus 6c2t dt. When we integrate with respect to t, we have c1 equals t cubed over 3 plus 2tc1 plus 6c2t squared over 2. The limits are 0 to 1. So when we put in our limit, we get this. And when we solve this and we simplify it further, we get c1 plus 3c2 equals negative 1 over 3. And we name this equation A. So we take c2, and c2 was given by integral from 0 to 1 b2 of t y of t dt, and b2 of t is t, there's it, and y of t is the whole of this. So we multiply the t throughout, and we get c2 is equal to integral from 0 to 1 t cubed plus 2tc1 plus 6t squared c2 dt. So integrating with respect to t gives us t power 4 over 4 plus 2t squared over 2c1 plus 6t cubed over 3. Putting the limits of integration gives us this, and simplifying further gives you this equation. That's c1 plus c2 equals negative 1 over 4, and we call that equation B. So Our two equations are this. Okay, so solving these equations simultaneously, you can use any method that you know for solving systems of linear equations. You can use the Cramer's rule, Gaussian elimination, or anything. So when you do that, you are going to get C1 to be negative 5 on 24 and C2 to be negative 1 on 24. So remember this equation that we had. Let me show you where we had it from. So this. Okay. So from this, since now we have our C1 and our C2, we can make substitutions, right? So now C1 is negative 5 on 24. Now C2 is negative 1 on 24. That means we have y of x to be equal to s squared plus 2 times negative 5 on 24 plus 6s times negative 1 on 24. This will give us minus 10 over 24. This will give us minus 6x over 24. So breaking this down further gives us y of x equals s squared minus 5 over 12 minus 1 over 4x. And this happens to be the particular solution or the exact solution to the integral equation that we had. Okay, so let's solve the second example, question 2. So the second example says that if you like, you can pause the video and try to solve question 2, and after that you go through the solution to see whether what you had was correct or not. I think that will be helpful. It can help you to see whether you really understand the concept or not. So let's solve it. It says y of x is equal to negative 8x minus 6x squared plus integral from 0 to 1 20x t squared plus 12x squared t y of t dt. So comparing it to the general form of our integral equation, the free or forcing term is this. Our investigative parameter lambda is 1 and the kernel is that. So you could see for this question too, our kernel has two terms. Hence, to show that our kernel is degenerate, you write it in this form and then do further analysis. So the kernel was giving us 20x t squared plus 12x squared t. So we have a1 of x, b1 of t equals 20x t squared. That means we can say a1 of x equals 20x and b1 of t equals what? T squared. That's what you can see here. And for a2 of x, b2 of t equals 12s squared t, we can say a2 of x is 12s squared and b2 of t is t. So that's also this. So since you've been able to write our kernel in that way, it means that it is degenerate, okay? So since it is degenerate, then the general solution is given by this. I think by now you should be familiar with this, where we call this our CIs, okay? So since we only have two terms, that means we can expand this, and it will give us f of x plus lambda e1 of x c1 plus lambda e2 of x c2, where this is c1 and this is c2. So I'm coming. So yes, so here our x are supposed to be t, okay? So and this is supposed to be t. Okay, so and this is supposed to be t, this is supposed to be t. All right. So you should know we have a is a function of x, but b is a function of t. Okay. All right. So making substitution, we know our free term is this. Our lambda is 1. Our e1 of x is 20x, c1. Our lambda is 1. Our a2 of x is 12x squared, c2. And our c1 is giving us this. Our c2 is giving us this. Because our b1 of t is t squared and our b2 of t is what, t. So now we have to look for y of t to be able to solve for c1 and c2. Put them inside this and we get our solution. So that means we have to do change of variables. Okay, so we have to change our x to t. That will give us y of t will be equal to negative 8t minus 6t squared plus 20t c1 plus 12t squared c2. So now we can put them inside this to find c1, put them inside this to find c2. We get a system of linear equations and we solve them. So making a substitution into c1 is going to give us this. Because the whole of this is y of t. So we multiply it through by t squared. And that gives us this. And after that, we integrate with respect to t. And that gives us this. So the next thing is for us to put in our limits of integration. So putting in our limits of integration gives us this. And this, we can work around it, okay, to get this equation here. So 4c1 plus 12 over 5c2 equals 16 over 5. We call that equation A. Then we come looking for our c2. So c2 was given as integral from 0 to 1 ty of t. And I did the whole of y of t. So we multiply through by t, and that gives us this. Then we integrate with respect to t, and that gives us this. So we then put in our limits of integration, and that leaves us with something like this. So the next thing is for us to work around it, do some rearrangement, and we get this equation. 20 over 3c1 plus 2c2 equals 25 over 6. So now we are having two equations here. And the two equations are 4c1 plus 12 over 5c2 equals 16 over 5. And 20 over 3c1 plus 2c2 equals 25 over 6. So solving these two equations simultaneously gives us c1 to be 9 over 20 and c2 to be 7 over 12. Okay? That means we can come back to this and put in our c1 and c2. So doing that will give us y of x equals negative 8x minus 6x squared plus 20x, then times c1, which is 9 over 20 plus 12x squared, c2 7 over 12. So this cancels this cancels this. Then now we end up with y(x) equals negative 8x minus 6x squared plus 9x plus 7x squared. So minus 8x plus 9x gives us what? X. And minus 6x plus 7x squared gives us what? S squared. So y of x equals s squared plus x happens to be the exact solution to that particular integral equation. So yes, this is how we solve an integral equation, a Fredholm's integral equation, when the kernel is degenerate. Okay, it has some similarities with when the kernel is separable. The only distinction is that for when the kernel was separable, we only find for one c, but here we find for different c's depending on the term that we have. Okay, so thank you very much. Our next lesson will be on they're using the Leibniz rule to convert Volterra's integral equation of the first kind to the second kind. So I'm going to Karen of a final year student of mathematics, KNUST. Thank you very much.